Hello friends, welcome to my channel. So in the last video of the filter series, we discussed about I gave you an introduction to filters, and I also told you that a frequency axis is a log scale. I suggest you that before watching this video, you watch the previous video to understand this video better. Okay, so I told you that a frequency axis is a log scale, and our y-axis, our vertical axis, that is our gain axis, is in dB, decibels. So plotting dB versus log frequency means actual plot of log gain versus log frequency. So any linear relationship will be displayed as a straight line. So our graph somewhat looks like this. This is our frequency and this is our gain in dB. Fine. So dB, the expression of dB is 10 log 10 P1 by P2, where your P1 is output power and P2 is input power. And in terms of voltage, your expression is dB 20 log 10 V2 by V1, or you can write V2 as V out, output voltage and input voltage. Okay, so in the last video I told, in this video I will discuss about minus 3 dB frequency. So what is minus 3 dB frequency? What is the importance of minus 3 dB frequency? Minus 3 dB frequency is important to us because it helps us to find the cutoff frequency, and also at minus 3 dB frequency the power delivered to the load has been reduced to half. So minus 3 dB frequency is also called the half power point. Basically our P is what? V square by R. So our V will be what? Under root PR. So I told you when F is F minus 3 dB. So the voltage at minus 3 dB will be what? You know that at minus 3 dB frequency the power delivered to the load is reduced to half. So P by 2 R, or you can write 1 by under root 2 under root PR. 1 by under root 2 is 0.707 under root PR. So the voltage at minus 3 dB frequency is 0.707 of voltage at the given frequency. So at minus 3 dB frequency the power is reduced to 1/2 while the voltage is reduced to 0.707. Fine. So our power is reduced to half and our voltage is reduced by 0.707. So this is the graph. Our gain in dB, and this is our frequency. Our graph is somewhat like this. This is our AF. AF is what? Our pass band gain. AF is called pass band gain. So For example, this is our minus 3 dB frequency, or you can say this is our cutoff frequency. Let it be FH. So at this frequency our gain will be reduced to 0.70 AF. Fine. So at this point is 0.70 AF, and this point is actually 3 dB from maximum gain. 3 dB below from maximum gain. Maximum gain is AF. Fine. So we will get good response till AF by root 2, meaning till here we will get good response. After that the gain will decrease sharply. Okay. Even your phase shift between output and input, like the phase shift between output and input, keeps changing with change in frequency. As your frequency changes, your gain changes, as well as your phase changes. So at critical frequency, that is your FH, this phase shift will be a specific multiple of 45 degree. Fine. So at FC, your phase shift will be a specific multiple of 45 degree. Multiple of 45 degree meaning 45 degree, 90 degree, 135 degree, etc. So for simple filters which are built with only one RC pair, there will be a phase shift of 45 degree at critical frequency. So one RC pair, phase shift of 45 degree. If you have an additional RC pair added to the circuit, the phase shift another 45 degree at the critical frequency, meaning 2 RC pair, phase shift will be 90 degree at critical frequency, and 3 RC pair, the phase shift will be 90 plus 45, which is 135 degree. Fine. And in many filters, your minus 3 dB frequency and the critical frequency, this one, okay, they are same. Most filters built with RC pairs without op-amp are that way only. FH is equal to your F minus 3 dB. But when an op-amp is used to add gain and positive feedback to a filter, this FH and F minus 3 dB are no longer equal. So with op-amp, your cutoff frequency is not equal to your minus 3 dB frequency. Now let's talk about normalized frequency response. So each filter produces its own frequency response. Such response can be more easily grouped, identified, analyzed by normalizing the frequency axis. Your frequency axis is a log scale, and you can easily group or analyze your frequency when you normalize your graph, when you normalize the frequency axis. And how do you normalize it? You divide all the frequencies. For example, this is our graph, and you have frequency 0.1, 0.2 to 1, and then 2, 3, 4, so on. So you divide all these frequencies by the critical frequencies. Whatever is your critical frequency, this one. You divide all the frequencies with this frequency. This can be anything, 25, 100, 100, 200, anything. So you divide this critical frequency by, how do you find this critical frequency? When the gain is 0.707 of the maximum gain. Okay, at that point, whatever the frequency is, that is your critical frequency. Or you can say your minus 3 dB frequency. So you find your critical frequency and then you call it critical only, because when op amp is used, your critical frequency and minus 3 dB frequency is not the same. So you say like this only, that your critical frequency, you divide all your frequencies with the critical frequency. So if you see, if you divide your critical frequency by critical frequency, what will you get? 1. So the critical frequency of normalized frequency response plot is 1. And your gain axis, the gain axis of a normalized plot is adjusted to set the passband gain to 0 dB. So your AF here is 0. How it became 0? When you subtract AF from AF, you will get 0. This means this may be accomplished by subtracting AF from each point on the gain axis. So all the gain will be subtracted by AF and your passband gain will be 0 dB in case of normalized frequency response plot. Fine. And when you want to denormalize it, you can find your F actual by F normalized into FC, because you divided by FC, and your AF actual by AF normalized into AF, sorry, not into, plus, because you subtracted AF from all the gains, right? So plus AF. So the composite gain and frequency response will somewhat look like this. This is your 0 normalized graph. For normalized graph, your AF is 0. So your gain will be somewhat like this, and your phase plot is somewhat like this. Here you have your gain axis, minus 10, minus 20, minus 30, and so on. And here you have your phase axis, 0 degree, minus 45 degree, minus 90 degree, minus 135 degree, and this one will be minus 180 degree. I hope you liked this video. I hope you understood what I taught, and now I will see you in my next video. Thank you. And if you like this video, then please subscribe to my channel. Thank you. Thanks for watching. Goodbye.